Okay, 20.5 is about fission and fusion. Up until now, we've looked at slow, natural radioactive decay processes: alpha decay, beta decay, electron capture, positron emission, and gamma emission. But there are completely different chemical reactions that can be induced to occur. These reactions will often involve isotopes that were produced in other nuclear reactions or in particle accelerators. So you've probably heard of plutonium. Now, uranium and plutonium are maybe the two most stereotypical radioactive materials. Uranium you can mine from the earth, and it's a metal that actually was put into use in everyday life. Glass was colored green by the addition of uranium ions before people knew that it was radioactive and posed a bit of a danger. And so uranium is a natural material. Plutonium is actually not natural. You'll never find a plutonium mine. Its half-life is too short for anything that is formed in a geological process to still be around for us to mine later on. The way you get plutonium is by taking a bunch of uranium and allowing it to react in what's called a nuclear pile, which is like a slow burning nuclear reaction. And all the alpha particles and beta particles and neutrons and other particles are all sort of joining together and recombining and making new nuclides. So the radioactive series that uranium ordinarily undergoes will become more diverse and produce new different things if you get enough uranium together to make a nuclear pile. Anyway, so plutonium, for example, is an element that you cannot mine from the earth. It's generated through other nuclear reactions. And plutonium is able to undergo itself nuclear decay that is different than the alpha decay and beta decay that we've talked about before. So I talked about nuclear piles, also particle accelerators. Okay, so particle accelerators are where you use electromagnetic forces to bring protons together, or to bring protons into a neutron, or other particles like, say, a helium nucleus or anything larger than that. And so you sort of force these things to collide with enough energy that they might combine or they might break each other apart, etc., in order to form new nuclides. Well, anyway, the first reaction that we want to look at is called fission. And fission is achieved by bombarding a large nucleus with neutrons. Those neutrons will get absorbed into the nucleus, and that will push it away from that belt of stability, and it will become unstable. And so it will then break apart, but instead of just losing a small alpha particle or emitting a beta particle, or instead it's going to be so unstable that it will break apart into two substantial fragments, plus some other things. And so fission is when a large nuclide breaks apart into two substantial daughter nuclides instead of into just one daughter nuclide and an alpha particle. So let's look at here. The PDF is showing sorry, one second. Okay, so the PDF is showing the chemical equation for the fission of uranium-235 when it absorbs a neutron. You'll notice it breaks apart to form a barium with a mass of 141 and krypton with a mass of 92, and plus it releases 3 new neutrons. So this is also illustrated in figure 20.9. We've got that figure up there. So this isn't alpha or beta decay, this is fission. It requires a neutron to initiate, and that neutron needs to have sufficiently low kinetic energy that it can get absorbed into the uranium nucleus. If it's going too fast, then it would sort of deflect off. And so you need neutrons that are going slowly in order to have this sort of reaction occur. And because of that, this doesn't happen naturally very often. There are a couple of really interesting cases where groundwater flooded a uranium mine, and the water acts as a medium that will slow down neutrons and allow this reaction to take place. And so there are some natural places where this sort of decay takes place. But they're really special, unique, ideal conditions. Generally speaking, if I have a sample of uranium-235, then it's instead going to decay through other means. It's not going to decay by a fission all on its own. You'll notice that each fission event releases 3 new neutrons. And those 3 neutrons can then go and trigger their own fission events. And so this is a type of reaction that can grow exponentially. It's called a chain reaction. And figure 20.10 just kind of shows how one fission event can lead to 2 or 3 more, which can lead to 2 or 3 more for each of those, and it can rapidly grow out of control. So the reaction of uranium-235 or plutonium-239 is allowed to escalate exponentially in nuclear weapons. So nuclear bombs and missiles will be engineered in such a way that most of the neutrons will go on and propagate this reaction. And that's going to release an enormous amount of energy in a very short amount of time. If you have gunpowder, for example, that's a reaction that's going to require breaking and forming of new chemical bonds. It's going to require an oxidizer. Early gunpowder required oxygen itself, and then things like TNT had oxidizer built into it. But even though they react explosively, it still takes time for those chemical reactions to occur. Well, the only thing that is required for fission is a neutron, which travels close to the speed of light after a fission event. And so these fission chain reactions in nuclear weapons, I don't have any numbers in front of me, but they happen incredibly rapidly. Just on a scale that you cannot achieve through regular chemical reactions. And then they release an incredible amount of energy, which we'll talk about in the next section. And that's what makes these nuclear weapons in a class of their own beyond conventional explosives. So, sorry, let me skip ahead. Oop. Okay, I don't want to go too far. So let's get rid of the PDF and we'll scroll this down a little bit so that you can see my face again. Okay, so in a nuclear reactor, however, we obviously don't want our nuclear reactors to be exploding. And so they are engineered in kind of the opposite way so that the reaction does not grow out of control. A nuclear reactor, for using in power generation, is engineered so that the reaction will continue at a steady pace, well under control. So figure 2011 sort of shows that. You're going to have what we call fuel rods, which are the uranium, and it's enriched from the natural uranium that has a whole lot of isotopes that are not very radioactive. It's enriched to have a higher percentage of uranium-235, which is the isotope which will react through fission. However, it's not pure uranium-235. So if you have pure uranium-235, then that would make a bomb. If you have something that's only 10% uranium-235, then that can be used as a nuclear power plant fuel rod. And if you have natural uranium that has less than 1% of 235, then that's not really useful in power generation at all. Anyway, so those fuel rods are uranium. The fuel rods are immersed in water, and the purpose of the water is to take the 3 neutrons which are released through a fission event and slow them down so that they can then go on and propagate the reaction. Also, the water is going to absorb all of the heat energy that is released, and that gets exchanged with a regular steam turbine generator. And so, you know, a nuclear power plant, just like a coal or an oil power plant, and virtually every power plant that's ever been built is ultimately going to be generating steam, which turns a turbine, which turns a generator to generate electricity. It's just a question of where you get your heat from. So you'll notice we also have control rods there. Control rods are made out of either carbon or zirconium, and those materials are chosen because they can absorb neutrons, but they don't react further. So zirconium will absorb a neutron, it becomes a heavier isotope, but it's still stable. And so they act as a way to sort of take neutrons out of the equation and slow the reaction down. What the operator will do is kind of monitor the temperature, monitor the rate of the reaction, and if things are getting too hot, then the control rods will be brought down in to jacket the fuel rods and capture a lot of those neutrons and slow it down. If the reaction is getting too cold, that's a problem too, so the fuel rods will, the control rods will be lifted up and allow more of the neutrons to pass between and into the fuel rods to speed the reaction up. So you've probably heard of the term nuclear meltdown. In a meltdown, that's when the reaction gets out of control. But the reason why it gets out of control is tied to its name. What actually melts in a nuclear meltdown is the uranium fuel rods. They've got a melting point, and this reaction is exothermic enough that if it gets going too fast, then it's going to melt those fuel rods. And once they're melted, then they're going to no longer be, they're going to be difficult to moderate with the control rods, right? If the fuel rods melt, then they're going to splash down at the bottom of the pool of water, and then the control rods can no longer reach them and effectively slow down the reaction. And so that's what a meltdown means. The fuel rods are literally melting. Now this is an old design for a nuclear power plant, and there are new power plants that have very clever fail-safes, and there are new power plants that operate on completely different principles. If you look at the history of nuclear power generation, there are some notable disasters. Chernobyl in Ukraine or Fukushima in Japan or 3 Mile Island in the United States are kind of the 3 notable ones. And considering how catastrophic each of those events could have been, there's been clever engineering improvements over the years, and by and large, nuclear power is actually a lot safer than we typically give it credit for. Of course, it's also still fraught with problems, and I don't want to get into pros and cons of nuclear power, but Chernobyl is by far the worst, and Chernobyl was a very old first-generation power plant. It was also a confluence of things that led to the Chernobyl disaster. Fail-safes that were in place in that reactor had been literally turned off because they were, I believe they're being inspected or tested or something like that at the worst time. So anyway, okay. And there's one thing that I forgot to mention, and that is how you have a nuclear weapon that is capable of exploding and doesn't have any mechanism in place to moderate or slow down that reaction. Well, how do you prevent it from exploding prematurely? So you're going to have one slug of uranium on one side of the missile, and then you have another slug of uranium that's shaped like this on the other side of the missile. And both of these are on their own small enough that most of the neutrons generated through spontaneous fission will leave and not continue to propagate the reaction. So they're what we call subcritical. So this is subcritical. It's too small to actually begin to explode. And so when a nuclear weapon is, when it goes off, then there will be a small explosive charge right here, just a conventional explosive that will propel one subcritical mass into the other. And then they'll fit together in such a way that now they become a critical mass, which means they're large enough to begin that chain reaction. And you know, within microseconds, all of that uranium is reacting and releasing its energy. So there's one more quick thing I want to say about fission. Sorry, give me half a sec. So that barium and krypton were the reactants that we talked about and that we had a figure for. But you'll notice here that fusion reactions can have different products. That's supposed to say fission, I apologize. Fission reactions can have different products. There's lots of different ways that a big nucleon like uranium-235 can break apart. And so the barium-krypton is the most frequent or the most common, but you can also have uranium-235 92 plus a neutron. You can also have it break apart into tellurium-137 Te52 plus, and we'll leave that blank, some other daughter nucleus, and in this case it releases only 2 neutrons. So how can we identify the daughter nuclide, which is another product of this reaction? Well, we'll balance it just like we did all of our other nuclear reactions. So we have a mass number of 235 plus 1, that's a total of 236. We'll take away 2 from that for our 2 neutrons, and take away 137 for the tellurium, and we're left with a mass number of 97. Okay, and then we have the uranium's 92 protons. 52 of them go to the tellurium. That leaves us with 40 protons left over for the other daughter nuclide. And you look on the periodic table, what is element 40? It is zirconium. So this is another pathway by which uranium-235 will undergo fission. So the other type of nuclear reaction that we haven't covered yet is fusion. Fission was all about big nuclides breaking apart into 2 smaller ones. Fusion is all about small nuclides joining together to form a bigger one. So these are fusion reactions, and fusion reactions are the sorts of reactions that power the sun itself. So if you look down at the bottom there, I'm showing a series of fusion reactions that take place in the sun. So two protons can be combined to form an isotope of hydrogen that has one neutron and one proton. And then you'll notice that there's also a positron that is emitted in that process. This is called deuterium. It's just an isotope of hydrogen. We don't usually name all of the different isotopes. Carbon 11, carbon 12, carbon 13, carbon 14. We just call them all carbon and we give them a number. Well, this is just hydrogen 2. But because of its importance, we give it a name. It is deuterium. And the nucleus of deuterium is called a deuteron. So deuterium technically is the whole atom. It includes an electron. A deuteron is the nucleus. And you may have heard of heavy water. So heavy water is water that one or more of the hydrogens in that water is actually a deuterium. And then the next reaction shows a hydrogen reacting with a deuteron to form this isotope of helium with only a mass number of 3, and then 2 of those isotopes of helium can go on to form helium with a mass number of 4, and that's a more stable form of helium and releasing a couple of more hydrogens. So this is kind of going on constantly in the sun, and it's why the sun is releasing energy, why it burns hot. There's another isotope of hydrogen. This is called tritium. And we've actually seen tritium before. It undergoes beta decay with a half-life of about 12 years. So tritium is just another isotope of hydrogen, and the nucleus of a tritium atom is called a triton, or a triton. Although this is the primary fusion reaction that happens in the stars, because stars are made up primarily of hydrogen, there are lots of different reactions that can sort of compound and grow on these. Heliums can combine, they can form lithium and boron and carbon and lithium can combine to form fluorine, and it just goes on and on and on. Depending on the size of the star and the stage in its life cycle, it may be producing a lot of different elements. The largest elements are generated only in the short cataclysmic events we call supernovas, where a sun no longer has sufficient radiative pressure to hold back against its own gravitational pull, collapses in on itself, generating enormous heats and pressures, and then those enormous heats and pressures sort of catalyze one final spurt of nuclear fusion, making all the heaviest elements that we know before the star explodes and casts off 90% of its mass. So these reactions require very high temperatures and pressures. I can fill a balloon with hydrogen gas and not worry about it undergoing nuclear fusion spontaneously, because the activation energy barrier for these reactions is so enormous. And so nuclear fusion power plants do exist. In fact, you can build a nuclear fusion device in your garage if you've got enough gumption and time, called a Farnsworth fuser, named after Philo Farnsworth, who also was a part of inventing television. So, but they do not generate more electricity than is required to operate them, and so they're not actually practical. Most of them, the best ones that are most promising for maybe someday being used for nuclear power generation are also enormously complex and expensive, and so fusion, although it releases a tremendous amount of energy, it's just so difficult to get the process started that it's not a practical source of energy for us right now. It's about 40 years away from being something that is implemented practically. And that's what people have been saying for at least 60 years or so. So who knows when fusion will finally be developed to the point where we see it in use to generate electricity for us. Fusion is also used in weapons. So you've probably heard of a H-bomb or a hydrogen bomb. In a hydrogen bomb, hydrogen is used as the fuel, not by combusting it with oxygen, no, instead by, by combining them to form deuterons and ultimately eventually helium, just like in the sun, according to those reactions down there. So an H-bomb is also sometimes called a thermonuclear weapon, and they're sort of like two nuclear weapons wrapped up together, because in order to achieve the high temperatures and pressures required to initiate fusion, there are actually a regular uranium fission detonation is used in order to confine the hydrogen and to initiate the fusion. So in a hydrogen bomb or in a thermonuclear weapon, it's like first the uranium bomb goes off, and that generates sufficient heat and pressure to initiate the fusion bomb. Okay, sorry to talk so much about bombs, but these reactions are the most energetic reactions that we've discovered to date as humanity, so of course they've been put to that purpose. We'll talk about the magnitudes of those energies in a moment.